Hello, welcome back. We're going to continue our discussion from my previous video about Taylor polynomials. Recall what a Taylor polynomial does from yesterday is we said that a Taylor polynomial can be used to approximate the value of a function for us. And what's a really neat application of it is that we can also use a Taylor polynomial to approximate an integral that can't be solved any other way. For example, let's say we wanted to evaluate the integral, the area under the sine of x squared curve from 0 to 1. So let's take a look at here. I graphed it here already. So we want to find the area from 0 to 1. Well, if I want to evaluate this, I can't. There's no way I can physically take the antiderivative of sine of x squared. It does not have an antiderivative that we can easily solve for. So another way we can solve this is to approximate this. So we can use Taylor because in a previous video, we showed that we can approximate the sine of x with the polynomial x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Now, what we're really saying here is that the sine curve and this polynomial approximate each other near 0. And that's really what a Taylor does. It says near a certain center, in this case 0, we can say that our polynomial function will mimic our sine curve. With that being said, how can we then write sine of x squared? Well, all we're doing is replacing each x with x squared. So now I have a Taylor polynomial that can get me sine of x squared. So this would be x squared minus x to the sixth over 3 factorial minus, of course, x squared to the fifth is just x to the 10th over 5 factorial. Now, why is it so nice for us? Well, now, since I cannot integrate sine of x squared, I can replace that with my polynomial instead. Now, it's not going to give me the exact value, but it's going to be very accurate and pretty close to the actual value. So integrating this, we would get x cubed over 3 minus x to the seventh over 7 times 3 factorial plus x to the 11th over 11 times 5 factorial. And we can evaluate that from 0 to 1. Now, using our fundamental theorem, we are going to not worry about the zero, just plug in the 1. And that's going to give us 1/3 minus 1 over 7 times 3 factorial plus 1 over 11 times 5 factorial. And this would be our approximate for the sine for our area here. And it's not going to be the exact value again, but it'll be a very close approximation. And in terms of even if I could integrate sine of x squared, this is still a lot quicker to even get. And for most purposes for our life, sometimes we only need really an approximation. Now, later on, we will talk about how accurate this is. And that's when it gets a lot more fun for us. We're going to discuss the accuracy of our approximation. And in this case right here, this is going to be less than 1 over 75,600th of the decimal off from the actual answer. That's the error in this. We don't have time in this video to take a look at that, but we will be seeing that later on. All right, so what is a Taylor polynomial? A Taylor polynomial, this is just a way to, again, it just approximate our a function. That's all it does. We call these an nth order, where n is what we call the degree of our Taylor polynomial. For the most part, it's like the number of derivatives that we've taken. Be careful. Sometimes people think it's the number of terms. Nope, nope, nope. N is just the degree of a polynomial. Given at a center x equals a, sometimes we'll use the letter C in some books to get the center. And we have this P sub n of x. This is just saying this is a Taylor polynomial of degree n. We can use t sub n of x as well. You'll see that in a lot of books. And what we wind up with is this little formula right here. Now, I showed you in another previous video how we actually generate this formula. Was a really ingenious way to come up with this polynomial function. This is what we call the Taylor polynomial. Taylor. All we're doing is the Taylor polynomial here is just going to generate a bunch of terms. And what the sigma here does, what the sigma does is it says it's going to add up all those terms. That's it. So let's take a look at an example. Here we have to find a Taylor polynomial of degree n equals 6. So remember, that's going to be the number of derivatives that we want for the natural log of x. So what we're going to do here is we want to come up with a polynomial that mimics the natural log of x near our center of 1, near x equals 1. So think about what the natural log function looks like near 1. And we want to come up with a polynomial that looks like that. All right, so here we go. Here we go. Let's kick this off. Let's have some fun. So we talked about my previous video. Yeah, we're looking for the nth derivative. So we got a number of n derivatives here. And the 0 says this is the original function, which is the natural log of x. The derivative natural log of x is, of course, just 1 over x, which I'm going to write this as x to the negative 1. Taking the derivative, we're going to drop that power, so we get negative 1 and subtract it, x to the negative 2. Now, I'm not going to write these as fractions here. You'll see why in a second. This is just laziness on my part, and I know what's kind of going to happen. So taking the next derivative, that's going to give us a positive 2x to the negative 3, negative 6x to the negative 4, and this becomes, of course, 24x to the negative 5, and I forgot to get the sixth derivative, so let's go ahead and shove that in there here as well. And if I bring down that 5, that's going to give us a positive 120x to the negative 6. All right, now let's plug it in. So this is the tough part. Now we got to plug in our center, use the center. Whoops, hello, can't spell center. There we go. Plug in our center to each one of those derivatives. If we plug in the 0, the 1, this is just like the natural log of 1, which we should know is 0. And plug in for our first derivative here, right? We're just going to plug it in. That's going to give me 1, negative 1, 2, negative 6, 24, and yeah, I forgot the last one again too. Negative, whoops, that should be a negative 120. There we go. Because it's 5 times negative 24, negative 120. Now, if you're really clever, if you're really, really, really clever, you should notice there's a kind of a pattern here. The first derivative right here, the first derivative, that is just 1 factorial. The same thing for the second derivative, 1 factorial, 2 factorial. 6 is just 3 factorial. This is 4 factorial, and this is just 5 factorial. Now, of course, they have different signs there, right? So, can't really read the factorial. Now, if you figure out what a factorial is, remember factorial is just saying we're multiplying, like, right? So if I have 5 factorial, 5 times 4 times 3 times 2 times 1. That's how we get the 120. All right, so that's going to become helpful for us later on. It really just to simplify. We don't really have to simplify right now, but later on it will be helpful for us just to remember those if we can recognize that pattern. So next, now we got to write our Taylor polynomial, and I did not give myself near enough room for this one. So let's have some fun. So our Taylor polynomial, our rule is very simple. It is our f of n of center over n factorial x minus our center to the nth power. So we are looking for a 6th-degree Taylor polynomial here. So the first thing we're going to do, let n equal 0. Let n equal 0. We said that was just 0, so I can just plug that in. Don't worry about that. That's just 0. Next one, hello, so keep it black. Next, let n be 1. Let n equals 1. The value of our first derivative, we said was positive 1 there. Sorry about that. So 1 over 1 factorial. And this becomes x minus our center, that's C, 1 to the first. Okay, and that becomes a plus. We're adding. Next, let n be 2. Very easy to do. If we let n be 2, the value of my second derivative is negative 2. I'm sorry, negative 1, sorry. And then we go minus 1 over 2 factorial, x minus our center to the second. Next, let n be 3, and you get the pattern here. That becomes plus 2 because it's positive over 3 factorial, x minus my center, which is 1 cubed. Next, let n be 4. And at 4, we got negative 6. We'll go minus 6 over 4 factorial. And this is x minus 1 to the fourth. Now, let n be 5. Now I'm on the next one, right? 5, so 24. So plus 24 over 5 factorial. X minus 1 to the... That's a weird looking 5. Let me see if I can fix that. There we go, 5. And then the last one, let n be 6, that's minus 120 over 6 factorial, x minus 1 to the 6. Now, if you're clever, and you are, remember this, right? So I'm going to zoom in here real quick. If I'm going to zoom in real quick, oh, there we go, there's me zooming in. There's my Taylor polynomial, nasty. Leave it like that, that's your answer. But if you want to be really fancy, remember this one right over here, this is just 1 factorial. There we go, 1 factorial. This is 2 factorial, 3 factorial, 4 factorial, and here's 5 factorial. Now, the reason why that's so nice to be able to do, of course, this is also 1 factorial. This was actually 0. Yeah, that's just 1. There we go. That's up there. So the reason why we like this, so let's go back to our glory days of Algebra 1 or Algebra 2. If I have 5 factorial over 6 factorial, remember, this is just 5 factorial. Always keep this. This is 5 factorial, and the bottom is just 6 times 5 times 4 times 3 times 2, or 5 factorial. Those cancel, and I get 1/6. So I can use that to really kind of simplify this. So our 6th-degree Taylor polynomial, let me write this in black here. So our 6th-degree Taylor polynomial becomes, leave the 0 alone, this first term just becomes x minus 1 minus, remember, this is now 1 factorial over 2 factorial, which is just 1/2 x minus 1 squared. Plus, same thing here. This is 2 factorial over 3 factorial, which is just 1/3. So this becomes plus 1 over 3 x minus 1 cubed. And again, this is 3 factorial over 4 factorial, which just reduces to 1/4. That's my rule up here. So this becomes minus 1/4 x minus 1 to the fourth. And you might be thinking, there's a pattern. Absolutely. 2, 2, 3, 3, 4, 4, and the signs are alternating. So we get plus, and again, keep going. This is 4 factorial over 5 factorial. This is 1/5 x minus 1 to the fifth. Minus, and again, the last one now is 5 factorial over 6 factorial, which is just 1/6. 1 over 6, x minus 1 to the 6th. And that would be our polynomial reduced one. So why do we want to reduce it? Well, that's the next part. See, down here it says, use our Taylor polynomial right here to approximate the natural log of 1.1. So we can say that the natural log of 1.1 is approximately, ready? And now we're just going to let x equal 1.1. So plug 1.1 into our polynomial up here. And that's going to give us 1 minus 1, or 0.1, minus 1/2 times, this is just 0.1 squared, whatever that is, plus 1/3 times 0.1 cubed, minus 1 over 4, 0.1 to the fourth, plus 1/5, 0.1 to the fifth, minus 1 over 6, 0.1 to the sixth. Now, again, this is an alternating series, and we're going to talk about this later on. So how accurate, you might be asking, is this? Ready? This is the accuracy right here. This is the accuracy for this one. Ready? It is less than 1 over 7 times 0.1 to the seventh off from the actual value. And again, we're going to talk about that later on when we get to what's called the alternating series remainder. And it's going to be a really cool thing to do. You're going to really like it. You can see not just how cool of a tool this is, but how accurate it is. And you might be saying, yo, but why don't we just use a calculator? Where's the fun in that? All right, I hope you enjoyed the video. Please see me in my next video. We're going to take a look at a bunch more examples. I'll see you then. Bye-bye.